Okay, so another thing that I wanted to look at in this section was how do then all these trig ratios present themselves as reduction formulae and their core sorry, that's just a mistake there, and their core ratios and the ratios and their core ratios.
Okay. Yeah.
Okay, so again here what we are looking at, we're looking at some reduction formulae and also the core ratios and the ratios and their core ratios. So again here, if we consider this Cartesian plane, for instance, if we look here, so this is where we have the angle theta, right? So here you can take this. If we have a sine of 360 degrees, remember we said that this is either 0 or 360 degrees. So, but if we have sine of 360 degrees plus angle theta, right? So what is this reduced to, right? So this is exactly the same as 360 and the same as angle 0. So now do you see that sine theta will reduce because this is in the first quadrant where all of these ratios are positive. So this will reduce to a sine theta, because you can think about this as just 0 degrees. So 0 plus degrees plus whatever that angle theta is, it will be then the sine of theta. And of course, everything here, if you remember from the cast diagram that we spoke about in the previous section, is that all of these things are positive, or these ratios are positive. So the same thing you can do for cos theta, which is 360 degrees plus theta. Again here it will be just the cos of theta, and here the tan of 360 degrees plus angle theta, which is now equal to the tan of theta. And here there's something that I want to explain, is that if we now decide to use this terminal here, which is that terminal 90 degrees, and again the same effect is experienced when you use 270 degrees, right? So that's why many teachers, they will tell you try and avoid not to use 90 degrees and 270 degrees, because what they have an effect if you use them, then what they do, they change their ratios into their core ratios, or they change the core ratios into their original ratios. For instance, if we take here the sine of 90 degrees minus theta. So, right, we're using that terminal. Again, we're still working with that, right? So now this here, it's a sine. So you can almost like, what that 90 degrees does is that, so the effect of 90 degrees, it will, if it's an original sine, it will give it a core, which now this change it into a cosine, right? So this will change to a cos of theta, right? But now if I am looking at cos theta of 90 degrees minus theta. So what this now, because now it has the core, then it will take away the core. And then, so if you think about it, this is a cosine. So if you take away the cos, then it becomes the sine of of theta. So that's basically what the effect of that. And please guys, but just be on the lookout all the time for that 90 degrees, or in this case you will see when we get to the third quadrant when we have 270. So the same thing we can do. I just want to run through this one quickly for the interest of time. So then if we have now, if we look at this, we have sine of here 180 degrees minus theta, right? And then we have again the cos of 180 degrees minus theta, right? And the tan of 180 degrees minus theta. And again here I just want to add two more, which is the sine of theta and 90 degrees. Now let's have a look. 90 degrees plus that angle theta, and that the cos of sorry, I made a mistake here. So it's 90 degrees minus theta. So if we have a look here, we remember from the cast diagram is that this is the only guy who becomes positive here. So this again 180 here, same effect as 0 or 360. It has no effect, doesn't change anything. So sine of 180 degrees, it will then be the sine of theta, and then it becomes a positive sine theta. Why? Because it's only sine that is positive on this quadrant here. So that's the first quadrant, that's the second quadrant, and this is the third quadrant, and this is the fourth quadrant. So again here, cos in this quadrant is negative, so do you see that becomes minus cos theta, and tan here in this quadrant again it's negative, right? It's negative tan theta. So if we look at sine again here, the 90 degrees plays the same devil it was before. It will change the sign to and give it a core, and then it becomes a cosine. But now we need to just be careful on this one. And please guys, I'm hoping that you are actually listening. First thing is that we ask ourselves, how is sorry, I made a mistake here. So this quadrant is not 90 degrees minus theta. So this is 90 degrees plus theta and 90 degrees plus theta. So here, so if we look at this here, it's going to be sine of 90 degrees plus theta. So on this one here, first ask ourselves, how is sine in this quadrant? It is positive. And then after that, we then say, what does 90 degrees does to sine? It then gives it a core, which is becomes a cos of theta. Again, the same thing here. Again, how is cos in this quadrant? It is negative. And what does then 90 degrees does to a core? It will take away the core, and then this becomes sine theta. So that's how these reduces to, so that such that it's only these two that are positive in that quadrant. So the same thing we can do. I just want to do this one quickly for sine of 180 degrees plus theta, and the cos of 180 degrees plus theta, and the tan of 180 degrees plus theta. And then again here, it's that we're gonna have the sine of 270 degrees minus theta, and then the cos of 270 degrees minus theta. So again here what we'll see, sine, how is sine in this quadrant? It is negative, so 180 doesn't have any effect, so it just becomes negative sine theta. So again here the cos in this quadrant is negative, so it's negative cos theta. And then the tan in this quadrant, and remember it was all stations to Cape Town. So now its tan is always positive in the third quadrant. So, and then if we look at the sign here, but now we're using the terminal 270. So 270 minus theta, what will it do to this? But firstly, we ask ourselves, how is sine in this quadrant? It is negative. And then what does that 270 does to the sine? It will give it a core, then it becomes a cos of theta. So again here it is the cos. Again, how is cos in this quadrant? It is negative, and then what does it do then? That cos to what does the 270 does to that cos? It take away the cos, and then you're left with a negative sine theta. So just for the last part, again here we can say a sine of 360 degrees minus theta. So 360 degrees minus theta, and here the cos of 360 degrees minus theta, and again here then the tan of theta, or rather tan of 360 degrees minus theta, and then the sine of 270 degrees plus theta, and then the cos of 270 degrees plus theta, right? So here, if we have a look at sine of this, the 360 has no effect on that because it's not really. So it will be sine. How is sine in this quadrant? It's negative, and then it's minus sine theta. And then the cos, how is cos in this quadrant? Is always positive, so that becomes cos theta. And then the tangent of that 360 degrees minus, how is tan in that quadrant? Is negative tan theta. And now let's have a look at 270. How is sine in this quadrant? Sine is negative in this quadrant, and now what does 270 does to sine? And then it changes and gives it a core, so then it becomes a cos of theta. And then the cos, again here, how's cos in this quadrant? It is positive, and then what does 270 does to core? Takes away to the cos, and then we're left with a sine theta. So that's how, guys, all of these reduction formula demonstrate themselves, or cause ratios demonstrate themselves, and that bit here does actually help us in order to try some of the examples that. But just before, I just want to add on just one bit before we can start our formulas, is I just want to add this bit about the special angles. The special angles, those of you might remember, is angles such as 30 degrees, 60 degrees, and 45, 45 degrees. So these special angles is that firstly you can you do not need to memorize them, but I've seen some students trying to memorize them. So let's consider here an equilateral triangle which has all sides that are equal. And then what we do is that if these all sides are equal, and then with the all equal angles, right? And for these, because remember all of these must add up to 180. So if you want all the equal angles, so you'd see that this will be 60 degrees here and 60 degrees there and 60 degrees here. So if we then cut, we put a perpendicular bisector here, this perpendicular bisector, it will give us 90 degrees there, and because it is a bisector, it will cut this into 1 and a 1, and then we need to find, using Pythagoras theorem, what this other side is. So it's r squared is equal to y squared plus x squared, and then here, so it's almost, if we think about this as y, this is r and this is x. So then what we want to do is we have r squared minus x squared is equal to y squared. So here that r squared is 2 squared minus 1 squared, and if we take the square root of that, quickly, I'm just jumping one more step here, so that gives us, it's going to be 4 minus 1, so that gives us a square root 3. So you don't need to really memorize this. So when you enter the exam, you can actually just, when you get into the section, you can quickly do this right on your side, so that you, on the side where you write on your scrap paper, so that you can remember again what is the sine of 60 degrees, what is. So when we cut this with that perpendicular bisector, it also cuts this into a 30 degrees and a 30 degrees here. So, but also another one special one, which is the easy one, is when you have that angle being exactly the same as this, and for these two to be equal to each other, that has to be 45 degrees, and that one is 45 degrees. So this is 1 and 1, and again here, if you go through this whole process, you'd find that this becomes square root 2. But also the other thing these days is that if you're using the Casio calculators, before you can press but I mean, the examiners, you don't need to do that, because they will always tell you without the use of calculator. But the point I'm stressing here is that if you do, you need to report your answers in this form here, if you're working with the special angles, right? So another thing that I wanted, just to, before we can go into our examples, is to talk about these three identities that you learn in grade 11, and which is required for your grade 12, is that you need to express your tangent of theta. Again, most of the time here, it must be that your tangent of theta must be sine over cos theta, sine theta over cos theta. And again, also another trick identity you need to understand is that sine squared theta plus cos squared theta is equal to 1. And if that is the case, then it actually follows that your sine squared theta is equal to 1 minus cos squared theta. And again here, if you're just looking for the sine of theta, it is, if you put a square root there, it will be 1 minus cos squared theta. Rather, that was theta. So again, here the same thing that you'd need to do if you're trying to explain cos squared theta. It will be 1 again here. If you take that across, it will be 1 minus sine squared theta. And again here, cos of theta is given by a square root of u 1 minus, sorry, I just made a little mistake here. So this 1 minus sine squared theta. So it's 1 minus cos, rather sine squared theta, right? So these are, if you look at some of the things that we've gone through here, these are all the things that need to go into your toolkit for that part in trigonometry, in order for you to be able to look at some examples. So in the next session, what we're going to be looking at is that how are all of these, how are these questions asked, or we look at some examples so that we can see how the examiners ask this thing for us. So okay, so I just want us to look at some of the few examples to try and illustrate some of the things that we talked about earlier. So from time to time, I'm just gonna refer you back to some of the things that we spoke about. So I want us to look at this question here, um, which is given. We're given that sine of 31 degrees. Believe it or not, this is 31 degrees, not 81 degrees. So if we're looking at sine of 31 degrees is equal to A. So from my experience, I've seen some of the students trying to work out this without, because they will read this example here and then read that instruction and read that question there, which is, that question says that write each of the following in terms of A, without, because the first thing that you need to do is to firstly to take that and use that to reconstruct a Cartesian plane here, right? So what we are looking at is that we're looking at the sine of 31 degrees is equal to A, right? So it means that if we now reconstruct on the Cartesian plane, so that's the y-axis and these are the x-axis, x-axis, and that is angle 31 degrees. And now what we are given is that we are given that sine of 31 degrees is equal to A. So we can rewrite this A here, remember it is actually the same as A over 1. So, and then again here, I just wanted you to listen carefully to me. But what do I mean by sine? Then again, it takes us back to the whole thing about SOHCAHTOA, which is sine is opposite over hypotenuse, right? So we can use this and then put them again here. So the opposite side being y, that's x, and this is our hypotenuse, which is r. So now here our y is equal to a, so, and then that a and the r vary here, which is the hypotenuse, is equal to 1. So now we can be able to work out using the Pythagoras theory that r squared is equal to x squared plus y squared. So this r squared is equal to 1, and x is what we're looking for, and then y is equal to a, right? So such that now we can define x squared is equal to 1 minus a squared, and such that now we know that x is equal to, now if we take a square root on both of those, and then if we take a square root of that and the square root of that, that gives us 1 minus a squared, right? So this here is now what the value of x is, and then we can take that x and then put it here as 1 minus a squared, and then we take a square root of that, right? So such that now I am able to now go and so I've seen so many students want to, they will look at this and then they will read this and then try, in a seriously confusing way, trying to figure out what will be a sign of that. But in order for you to be able to work all of that stuff out, you need to start by reconstructing the Cartesian plane and then put in the information here. So let's start, for instance, here for sine of 149 degrees. So now if we're looking at sine of 149 degrees, do you agree that it is actually the same as 180 degrees minus 31 degrees, right? So now we've transformed this and we've expanded into something like this. So now this tells us here, this is which quadrant? It is the second quadrant. How is sine in that quadrant? So the sine in that quadrant is positive. So it's positive sine of 31 degrees. So now if you try and follow this, the sine in that quadrant is sine of 31 degrees, and then the sine of 31 degrees there, it is now opposite, which is a over hypotenuse, which is 1. So it's still a positive a. So we've explained that in terms, so that's for our a. But if we're looking at b, which might be a little bit more trickier, right? So again, I wanted to take you back to that section where we spoke about this here, this being the positive direction, right? With moving anti-clockwise, you're moving in the positive direction, and moving clockwise is moving in the negative, right? So if we're looking at cos of minus 159, so let's write that down. So it's cos of minus 59 degrees. So if I am looking at this, so now I will be trying to explain that, right? But now one thing that I see, if this is minus 59, and then if we can just reconstruct this, so for you to make sense, if this is now minus 59 degrees, so do you agree that this bit here will be 31 degrees, right? So I need to explain, because I have information about a sine of 31 degrees. So now do you see that this here is actually the same as angle minus 90 degrees plus, right? So if I'm looking at this terminal, remember we said 270 is exactly the same as minus 90 degrees. So if I'm saying minus 90 degrees in the move in this direction, it's a positive. So now do you see that that's exactly the same as plus 31 degrees, right? So then that is cos of that. But now, so if I've expanded this to this, so the two things that happened here, I need to find out first, how is cos in this quadrant? And if I look here and say plus that, so this is the fourth quadrant. So this is the fourth quadrant. So then the cos in this quadrant is positive. And what does the 90 degree does to that cos? It swallows away again the core, which means that I'm now left with the sign of 31 degrees. Again, here it is a positive, and then the sign of 31 degrees here, and then the sign of 31 degree. It will give me, again here, if we look at this, the sign is opposite over hypotenuse, so it will be positive a over 1, which is just basically a, right? So that's what it does for, I just want to run through quickly C and D, and hopefully then I'll leave up E for you to do on your own. So again here, just for us to be able to see what's going on, then they ask me what is the cos of, for the C, cos of 329, right? It will be an easy one, isn't it? Because now if we look at that, that's 329. So if we looking at that 360 minus 31, you can punch that out of your calculator, that this is cos of 360 degrees minus 31 degrees. So then that is, now if I'm looking at this, this is the fourth quadrant again, and then in that fourth quadrant, how is cos there? Is cos is positive, and what does 360 do? It does no effect to that, because remember it is this terminal here, which has no problem, right? So it's 360 degrees minus 31. So we said that's the fourth quadrant, so that's now give us the cos of 31 degrees. And again here, if we go back, because you didn't reconstruct this and you did your Pythagoras theorem here, you would have had a problem, because now if we're looking at this, what they're telling us is that cos is adjacent over cos is adjacent over hypotenuse. So adjacent is being x over r, and x being, if you remember here, we worked it out, it became the square root of 1 minus a squared, and then divide that by 1. So therefore this is now equal to just the square root of 1 minus a squared, that is positive. So that sort of help us. So I just want to run through quickly to D before we can so D, we're given that it is 10 of 211 times the cos of 211. And you'd remember again here, from that section that it's really up to you. But remember when we spoke about some of these identities, as soon as you can see the tan there, what do? So we change that into a sign of 211 divided by the cos of 211. And of course you can only do this if there's two, if that is still the same, so as the same angle. So this becomes a cos of 211, and which now makes your life much easier because you can cancel that out. And basically what are they asking from you is what is the sine of 211. So again here, let's work out what is the sine of 211. So do you see that if we take this again here, that's the line 180 and then plus 31. So you now see that this is actually sine of 180 degrees plus 31 degrees, right? So this again here we ask, what quadrant is this? It is the third quadrant. And how is sine in that quadrant? It is now a negative, right? The sine, so it's going to be negative sine of 31 degrees. And again here we go back, we now try and find out how is the sine of what is the sine from this reconstruction that we've done here, is that the sine of 31 degrees is equal to a positive a, so it's just a, so therefore it will be just negative a, right? So pretty much then you can just do that easy one about the tangent of 31 degrees. But another thing that I thought it will be very important for us to look at, it will be very important for us to look at is the is the second one here. I just wish to try and do it here. What we're given, we're given that P is equal to the sine of angle beta. Again here we're not being fancy about that. So if we're given that, right, so you can also again on the same as the other one, we can express this as sine of beta is equal to P. And same thing that we did with that other one here, sine is opposite, so P is just P over 1. This is opposite over hypotenuse, right? So then that's same as hypotenuse. Again, as soon as we've done this, we go and reconstruct our Cartesian plane here. Sorry, I just messed up my writing paper here. And here, so again here we can reconstruct this, and then we call this angle beta, right? So this is our y, this is our x, this is our r, and r here happens to be equal to 1, the hypotenuse, and the y is equal to p. So again here you can do quickly your Pythagoras theorem. So it again, r squared is equal to x squared plus y squared, and easily here we'll know that x squared is then given by 1 minus r here. sorry, it's 1 minus, and then y squared is equal to p, so that's p squared. So therefore x is equal to the square root of 1 minus p squared. So now this, we can now go put this into square root of 1 minus p squared. So, and then as soon as we've done that, so now we can now take that and put it down again here, that it is cos of beta, right, plus 360 degrees, and again the tan of beta, right, minus 360 degrees, minus 360 degrees. 360 degrees times the cos of beta plus 90 degrees. So, and then all over sine squared of beta plus 180 degrees times the cos of beta, right, minus 90 degrees. And again here, I just want to take your focus back again what the examiner wanted me to do here. They've asked me to express this here in terms of p, right? So the first thing is, I could do this in two ways. Is I could firstly reduce these, right, into a single trigonometric ratio, and then I can be able to work it out. Or I could do it directly from here, and replace what your what is the cos of this, what is the tan of this. But to be just quite simple with ourselves, first is, then the first thing is that we need to define what quadrant is this, what quadrant is that, what quadrant is that, what quadrant is that. Here it really doesn't matter what quadrant it is really, because that's just the squared. So if I then have asking for myself, what is cos of beta plus 360? So here I have that's the angle beta, right, and then plus 360. So plus 360 here takes me back to here. So do you see that that is still quadrant number 1? So there, and then if I go all the way back here, it takes me back to the same thing. But again here, what is beta minus 360 degrees? What quadrant is that? So that's angle beta, and minus, now minus means that I must go in that direction. So it's that minus, and then it takes me back again to the first quadrant. So the most important thing is for me to identify which quadrant is it for each one of this. So again here, tricky, cos of beta plus 90 degrees, beta plus 90 degrees, that take me to the second quadrant. But I have another problem here, because this guy here is 90 degrees, right, communicates something to that core. So as much as I need to find out first how is cos in that quadrant, and then now I need to do first to again deal with what does 90 degrees does to that. So this is a really perfect example that just try to bring out all of these reduction formulas and the core ratios and the Cartesian plane and the Pythagoras theorem to try and put it into one one example here. So if we have then the sine squared, as I said here, it has no difference whether it's positive or negative because there is that square. But let's just have a look. So if we had a beta plus 180 degrees, that takes us to the third quadrant, right? I'm hoping guys are following. And then I have beta minus 90 degrees. Again here, that's my angle. Beta minus means that I must go in that direction, 90 degrees, which means you see that I'm sit on the fourth quadrant. But again here, what does this 90 degrees does to this? So I must be also mindful of that. So let's just start with this first quadrant. Everything is positive, so I have a cos of beta times and then I have now the tangent of, again here, if I go right around, I go back to the same. So I have the tangent of beta times the cos of this. That's the second quadrant where this cos is negative. So I put my negative there, and then what does the 90 degrees does to the cos? It takes away the co, then I'm left with sine of beta, right? And then I am then left with the sign here. Though sign is negative here, it has no effect because that is still squared. So if I square that, so then that, if I square this again, that still sit positive. So as much as it will be negative, so this will still be remain as sine squared beta, and then the cos here, and this cos here, what does it do? So the first thing is that what quadrant is that? We said it's a fourth quadrant. How is cos in that quadrant? It is positive. So let's just put that cos is positive. And what does the 90 degrees does to the cos? It changes to a sine theta, or rather sine beta. Sorry, I just let my brain slip off there. So, and then the next thing, what did they tell us we must do? We change the tan beta. So if we change that, saying here is that on the next step is then we need to look at, we had a cos beta there. So that becomes cos beta over 1 times the 10, and remember what I said is that with the tan of beta we need to change that into sine beta over cos beta, then times that by, remember what we said here, so that's minus sine beta, so it is equal to minus sine beta, and then all of that over sine squared beta times a positive sine beta, right? So if you remember from here, that becomes positive sine beta. So this cancels out with that, and so that here on top we're left with sine beta times sine beta, so it's minus sine squared beta. So we can cancel all of that with this, and then we're left with the negative on top. Then that whole, if we try and find another space here, so we said it's negative 1 all over right? The sine squared beta cancel out with the top there. It's over sine beta. So if we go back to what we were given first is, so if we go back here, is that we were given that sine beta is equal to b. So now our answer is, right, minus 1 over sine beta. And sine beta, remember, it's equal to p, so it's minus 1 over p. So therefore this is minus 1 over p, right? So now we've expressed that. So we've expressed this whole thing here in terms of p. So I just want to leave it here for now, and then on the next section we're gonna deal with the trig functions and the compound angles and double angles. But here, before I leave you, I just want to leave you with right, with these ones here that you can do as a practice at home. So I want you to take again here, when you take all of this, to try and prove these identities, that is reduces to 1 minus 10 alpha, so and so on, all the way up to f. That should give you enough practice. So that pretty much takes us to most, and I've tried here over, and you can appreciate that that takes a little bit of a process, which we've taken through just doing this video, is to actually just try and understand those basic things that we've learned in grade 10 and grade 11. So in the next session, then I'll try and so for now, what I would like you to do is to leave you with this, and then you can actually do these at home, and then on the next video then we'll deal with all those things that is required of us that we were taught in grade 12. Okay guys, I hope that this session has been very helpful to you. Like I've said before, what we are trying to do is to try and cover the work that you've done for grade 10 and grade 11, to squash it into one video. So if it felt like a bit exhausting, that's really understandable. But like I've said in the introduction before, if this has been helpful to you, so please just be in contact with us. Our numbers are appearing on the screen as we speak, and so please ask your parents, beg your parents to just to, so that we can send you some more videos of the same. Otherwise, I will catch you on the next session, where I'll still be dealing with some trig work, but more importantly, all those things that you were being taught in grade 12, which is your compound angles, your sum part of grade, sorry, trigonometric functions, but also double angles. So we're going to be looking at some of those things that will be examinable in your final exam paper. Okay, thank you very much.